Now let's talk about how we would use MATLAB's built-in function ODE45 to solve a system of differential equations numerically. Before I jump into that, let's just review what we've learned about this function so far. So we use this function to solve a single ODE. Y dot is some function of t and y. And the way it works like this. In MATLAB, you first define the function f, which is the right-hand side of that equation. So I would type something like f is equal to a function of t and y, and then whatever it is, the particular function goes here. So I have to first define the function. I have to give it a list of times. And an initial y value. So I would do something like times is equal to t-min, whatever I want my minimum time, my time step, and my maximum time. So I'm going to give it a list of times that I want to know the function y, and then I call the ODE45. ODE45, sorry, let me put it over here. ODE45 comes with 3 arguments. The first is the name of the function, f. The second is the list of times that I want to know the value of y. And then the last one is the initial value of y. It will give you 2 lists out. So I usually store them like this: t solution, y solution. So I've got here my list of times that I want to know the function y. This is my initial value. That's my function name. And then my solutions are stored here. My list of time points is in t solution, and my list of y points, that's the ones I really want to know, are in y solution. So now what I want to do is talk about how do we adapt this, or how do we use this if I have a system of 2 equations. So how do we use ODE45 to solve a system of 2 ODEs, or 3 or 4 numerically? So here's my system of ODEs. I've got 2 functions, f1 and f2. To understand the way MATLAB works, you have to start thinking in terms of matrices or vectors. So what I'm going to do is I'm going to write this in vector form. So write the system in vector form. So I'm going to write it like this: d by dt on the left side, and I'm going to have x and y here is going to be equal to f1 of tx and y and f2 of tx and y. So the top row is the first ODE, and the bottom row is the second ODE. And then to make the notation really compact, I'm going to call this vector, I'm going to call it u, vector u. So u is a vector. The first entry is x, the second entry is y. And I'm going to call this thing on the right is also going to be a vector. So let me call this whole thing capital F. T. And it also depends on u, right? So because it depends on x and y, but x and y are pieces of u. So therefore, I can write this whole system of differential equations in this kind of compact form. U dot is equal to some function f of t and u, like that. So that looks like a first order ODE, but it's just actually several ODEs kind of written very compactly. But this is the way that MATLAB understands how to solve ODEs numerically. Okay, so how do we use ODE 4.5? I need to do the same steps as I did before, so I need to define the function f, but it's a vector now. So I'll start the same way as before. Say f is equal to a function of t and u. So this is the same as before. I'm defining it's a function. And then the thing is that f is a vector, so it has two entries. So I need to put in here f1 of t, u1, u of 2. That's the first entry. And then f2 of t, u1, u2. Okay, let me explain what's going on here. I'm giving it this vector f, and it has two entries, f1 and f2. So there's the first entry, and there's the second entry. So that part is straightforward. The tricky part is that I don't want to put just x and y here because it doesn't know what x and y are. I need to put x and y in terms of u. So the part that took me quite a while to get my head around is that x and y need to be rewritten, or I'd just say be written in terms of u. So x is the first entry of u of 1, right? So x is here. That's the first entry in the vector u. And y is the second entry of the vector u. Y is here. That's the second entry. So everywhere in this ODE that I see x, I should put u in brackets 1, the first entry of u. And everywhere I see y in the ODE, or the system of ODEs, I should put u in brackets 2. That's the hardest part. So you define that function. Okay, then everything else here is the same as before. Provide a list of times. Tmin, Tmin, Tmax, Tstep. And I provide an initial value, u0. It's going to be x0, y0. So this is my initial values. And then I call the thing as before, call ODE 4.5. And it works like this. T solution, U solution. Everything here looks exactly the same. ODE 4.5. The capital F, the times, and U0. Okay. Again, all the solutions are stored here. And then everything else is pretty straightforward. So really the hard part is this part, is writing the right-hand side in your system of ODEs in this form. That's the part that's the trickiest. After that, the modifications are very, very straightforward. One thing that I should mention is that U solution is a vector, of course, right? It's this vector up here. So if you want x solution, or the solution for x of t, are the first column of U solution, and then the Y points are in the second column. Okay. So just make sure that you're aware of that. So U is a vector. It gives you a vector with two columns. The first column is X, second column is Y. Okay, so it's all pretty schematic here. And again, we'll do some examples, but I'm going to save the examples for the end of the lecture when I start doing second order equations.